uh, various algorithm design paradigms, high level techniques, high level guidelines for designing algorithms. The first technique that we have studied in last class is called the divide and conquer paradigm, and it goes like this: divide the input into smaller subproblems, then conquer the subproblems recursively, and then combine the solutions for these subproblems to obtain uh, a solution for the original problem. So what are some of the examples? So here some examples, example problems we had seen is merge sort. These algorithms are based on this divide and conquer paradigm: merge sort, quick sort. Then we had Karatsuba's multiplication, Karatsuba's algorithm for multiplying two n bits numbers. Then we had seen Strassen's algorithm for multiplying two n cross n matrices. And so on. So today we will start another very powerful algorithm design paradigm, which is called greedy algorithms. So write this way: greedy algorithm. So what is greedy algorithm? What is the framework? On a high level, the idea of a greedy algorithm is construct solution iteratively via a sequence of irrevocable decisions. So on a high level, greedy algorithms looks like a iterative algorithm. It has a for loop or while loop, some kind of a loop. And in every iteration of the loop, the algorithm is making some decision, and which will not be altered in later iterations. In later iterations, it is sort of irrevocable or myopic decisions. And this is the feature of greedy algorithm. And we hope that, so what is the hope? That the final solution is optimal. Is optimal. Okay, so whenever we have an algorithm design task at our hand, typically we have three steps of algorithm design. So steps.
Sir, what are irrevocable decisions?
It means that we'll see in the example that, but it means that a decision taken in the first iteration that something will be part of my solution. Later, we will not change that decision. So think of a coin change problem, and you thought of an algorithm, a greedy algorithm, and in the first iteration, you decide that I will pick a coin of the denomination 10. Now, in later, you won't say that, although I decided in the first iteration that I will pick a coin of denomination 10, now I am changing that decision. No, that's not the case. Whatever decisions we are taking at each step, we won't change it. irrevocable or
How would we
myopic.
know? How would
Yes,
we know that like the thing we are doing is
correct. One. How do you know? Please complete your question.
so I wanted to ask, how do we know that the following this th
Sorry, your voice is breaking. How do you know? See, I can still read till this point. Sorry, I
hello,
can't
sir?
hear you. Yes, yes.
So I wanted to ask, like, how does following this method gives us the correct solution?
You have asked a very important question. I'll come back to it. I'll come to it. Okay. So whenever you have an algorithm design task at hand, typically this algorithm design process has three steps. First step is design of algorithm. Second step is proof of correctness. And the third step is performance analysis, like what is the running time, what is storage complexity, and so on and so forth. Performance analysis. Analysis. Okay. Now let me contrast these steps for greedy and divide and conquer. So this is divide and conquer. Divide and conquer. And this is greedy. So if you carefully look at the divide and conquer based algorithms, like we have seen, like for example, March sort, quick sort, Karatsuba's algorithm, Stressen's algorithm, this step, the first step is non-trivial. Designing the algorithm is non-trivial. For example, if you look at Stressen's algorithm, the main non-triviality is in design of algorithm. Then then proof of correctness is typically not difficult. It boils down to solving a recurrence. So let me, and you are all masters of solving recurrences. So let me write it easy. For divide and conquer, typically, sorry, not proof of correctness. Proof of correctness is sorry, just a minute. So performance analysis is easy because typically it boils down to solving a recurrence relation. And you all know how to solve a recurrence relation. And proof of correctness. For example, what is the proof of correctness of March sort or Stressen's algorithm? It's trivial by design. We do not ask also what is proof of correctness. It's by design. So it is, let me write trivial. Trivial or obvious. Let me write obvious. Or clearly visible. Let me write this way. Clear. Proof of correctness. The correctness is clear. There is nothing to prove. On the other hand, for greedy algorithm, designing design of an algorithm, we'll see all these things. Designing is easy. Performance is will also you will say very easy. Typically, it's an iterative algorithm, and so you need to study the runtime of for loop or while loop. Typically, it's very easy. The only non-triviality is proof of correctness, as some of you have already asked, just asked. How will I know that the steps, the decisions at every step that I am taking, which I will never change in future iterations, will lead to an optimal solution. So this is um, the non-trivial part. And what makes our life both interesting and difficult is that most greedy algorithms are not correct. They look correct, but they are not correct. We'll see examples. So this is a very pertinent question. How, as some one of you have asked, How will I know that this algorithm is correct? What do you mean by correct? That we are taking an irrevocable decision at every step, which at that particular iteration looks sort of a good thing to do, a best thing to do. But how will I know that at the end? Uh, at the end, I am also happy that yes, I have ultimately I have the optimal solution. I have an optimal solution. So that needs a proof. And this is a very um, uh, warning. You will see this often. Warning for greedy algorithm. Most greedy algorithms, let me write this way. Greedy algorithms are incorrect. Especially if the greedy algorithm yeah, not especially means why it is most non-trivial to prove correctness, and it is and typically the proof of correctness is often buggy. You will see that you will many of you will be able to prove that your algorithm is correct, only later to discover that no, it's your algorithm is not correct. And that's often because of our human tendency. If I design an algorithm, I have an affection like a mother towards her child. That yes, this is my algorithm. It should be correct. I have tried so hard. It looks correct. It's just that I need to prove it. And okay, I'll prove it. But be very careful. Most of the thing is wrong, especially if it is your algorithm, because then the affection um, towards your idea can blind you. Okay, so enough general framework. Let's go to an example. So our first example is a scheduling problem. So a scheduling problem. So let me reiterate, your focus in this algorithm design course, especially in the current context, should be the process itself, not a particular greedy algorithm, or for example, not a particular divide and conquer algorithm. You must care closely observe the process of how we are designing the algorithm, because both in exam and in real life, either in research or research career or in industrial career, you will not be solving these problems. You have to solve your own problem, and this process you have to learn, and that's the most important thing. Okay, so what is this problem? We have input n jobs, say 1 to n. These are the names of the jobs, and their lengths. Length is say L1 to Ln. These are integers. Okay, this greater than 0 if that helps. Although, yeah, this greater than 0. Non-zero integers. These are lengths, and each job has a weight. Say W1 to Wn. Assume these are also positive integral weights. Okay. Now, and there is only one machine. So the output is a schedule of a schedule. Right this way. A schedule which minimizes say uh, weighted sum of completion times. Weighted sum of completion times. That means you are executing this job according to a permutation of the jobs in some sequence, and you find which job completes at what time, and you minimize the weighted sum of those completion times. So example, let's see an example. So suppose, so what do you mean by that? Suppose there are 3 jobs, say 1, 2, 3, and their lengths L1 is say 5, L2 is say 2, and L3 is say 3. And their weights are suppose W1 equal to 1, W2 equal to say 2, and say W3 is also 1. So what is a schedule? A schedule, you have to decide on which order you will perform their jobs. A job once started cannot be stopped in the middle. It has to be executed till its end, till it finishes. So a possible schedule is so a schedule, so call it sigma, could be that first I execute job 2, then job 3, then job 1. So it's a permutation of the jobs in which order I am executing these jobs. Okay. So what is the completion time for, so if I sort of pictorially draw it, this is the time axis, time here is 0. First I execute job 2 and it takes 2 units of time. Then I execute job 3 and it takes 3 units of time. So this must be 5. And then I execute job 1, it takes 5 units of time, so this is 10. So completion time of the first job according to sigma will be what? When does the first job finishes? It's 10. What is C2 of sigma? 2. And what is C3 of sigma? C3 of sigma is 5. These are the completion times. What is the weighted sum of completion times? I need to multiply these completion times with corresponding weights. So W1 C1 of sigma plus W2 C2 of sigma plus W3 C3 of sigma. So this is sort of an objective function. We want to minimize this. We want to find a sigma which minimizes this sum. So for example, for this particular sigma, what is this? W1 is 1, say this is 10, plus W2 is 2, 2 times C2 to 4, plus W3 is also 1, and that is 5. This is 19. If you take a different sigma, a different sum may arise, and the objective of the function is to find, objective of this program, of this problem, is to find out a sigma which minimizes this weighted sum. Question on the problem statement. Before embarking on the solution or for any question, you first make sure that you understand the question. Is the problem statement clear? There are n jobs with given lengths of each job and their weights. We need to find a schedule which is same as the permutation of the jobs, which minimizes the weighted sum of completion times.
Sir, can you scroll upwards once?
Yes, that's why I always like the big blackboards in the classroom. This is the problem statement.
Okay, sir. Yes, sir, I've seen it. Okay.
Okay. Now can someone propose some greedy algorithm to solve it?
Probably
So the
The
job with
minimum
the largest weight
least
will be
weights should
done first.
be, yes,
Yes, least weight.
Least
least
weight
weight
should
should
be
be done
done
at the
last.
last. The last.
Okay. So the first candidate algorithm is that sort the jobs according to the weights and um, in say so for the time being let's assume that there is no ties. That means all L1 to Ln are distinct, all W1 to Wn are distinct. So the first candidate algorithm is that sort the jobs according to weights in increasing order and do the jobs in that order. Is that what someone was telling?
Sir, I
Decreasing, sir.
think
Means
I
the
think we should.
highest weight will be
I
done
think
first.
Sir,
Highest what should be done first. Correct, correct. Yeah.
sir,
That's one candidate algorithm. Yes, someone else was
I
telling.
think I
maybe we
should
have to
sort
find the
them.
ratio of Wn by Ln,
Yes,
and we have
ratio is
to.
one candidate. Correct.
Sir, I
So
think we
some
should sort
yes,
with respect to the product WL, WILI.
WILI. So these are the candidates. So first candidate is sort W sort WIs. Second candidate is so you see that's what I mean that designing the greedy algorithm is very easy. Design of an algorithm is easy. Second, someone told that sort WI times LI, these products. Third was sort. Someone was told WI by LI or something like that.
Yes, sir.
WI by LI. Any other candidate?
So we sort Wi times summation Li and then choose accordingly.
Sort WI times summation L1 to Ln.
Yes, sir.
But isn't it similar to like sorting Wi, because summation L1 to Ln would be same?
Correct. Very good.
Oh,
So
yes,
these two are
sorry, sir.
same. 1 and 4 are same.
Yes.
Very good. Because summation this is same. So 1 and 4 is same. Okay. Now relax the assumptions that okay WIs can be same also. Now or LIs also can be same. We'll see. We don't need that assumption right now. Okay. Now let's see one by one. The first algorithm sort WIs. Is it correct or so either you give a proof of correctness or to prove that it is wrong you give a counter example. We are considering the first candidate. The first candidate, is it correct? Either give me a proof of
So
correctness.
we could have
Sir, suppose there are two jobs,
Mhm.
and for the first job has like weight one and time, and the time taken is say 10, and the second job has weight 10 but time taken is say 1000. Sorry, I meant the reverse. I mean L1 should be 1000 and L2 should be 10.
Now what will the algorithm will do? Algorithm will do the 10 first, right?
Yes, but
Yes,
the
sir.
reverse order is correct in this case.
Is it? This is 10, this is 1010. In this case, what is the weight? 10 times 10, which is 100, plus 1010. And for the reverse one, 1, 2, and this is 1000, and this is 1010. So this is 1000 plus 1010 into 10. Oh, this is much better. This looks fine, right? For this example.
Oh, yes.
Yes.
Sir, the completion time is summation of Li to the ith point. So the one with the minimum Wi will give us the minimum result for Wi into the summation for Li.
No, I'm not getting it. So are you proving that this fast approach is correct? First, tell your answer. Is it correct or not correct?
So
What is this?
I think it's correct because
It's correct.
as we can see, the completion time is summation of all the times that has been all the work time of work that has been done before that. So so at the end of the day, it's if we consider the last time, it will be C1 into summation of all Li, W1 into summation of all Li. So as it is summation of all Li, the one with the minimum Wi will have give us the minimum sum for that.
It sounds reasonable. No, sound intuitive. Anyone want to contend his argument? He says correct and gives a sort of intuitive proof. Anyone want to contend? Or everyone is convinced that this is correct?
But in the case where maybe we have a lot more number of jobs, we have 100 jobs, and out of those 100 there are 99. There are a lot of jobs which have a greater weight but take a very less amount of time. Then we would end up so actually the opposite. We have a lot of jobs which have a high weight but a very low amount of time. They would likely take up a lot of time, and then we would start doing the job which takes the longer time. So
but are you saying that this is not correct? This approach is not correct?
yes, I'm saying this is
Can
not.
you give a concrete counter example?
I would like to give one.
Yes.
So suppose there are two jobs. Okay.
First, you tell me what are you proving? Correct or incorrect?
I am proving that sorting of is not correct.
Not correct. Okay. Now give me an example. So this example is not working. Shall I erase this example?
Yes, sir.
Okay.
So for example, there are two jobs such that the product of W1 and L1. Okay.
Give me a concrete example.
Okay, I mean the exact set. Okay, W1, L1 is greater than W2, L2, but W.
That is the thing. Typically, whenever you want to prove some concrete statement is not correct, you have to give me a concrete example, like numerical example. On the other hand, to prove that something is correct, you need to give me a formal proof. Yeah, both are formal. Yeah, tell me.
So for first one, we should disprove, right? Sort WIs.
I don't know. You tell me. If so, you are saying it is.
No, I have an example. I think we can disprove the first one.
Okay, tell me the example.
Like you can take two jobs with W1 as 2 and L1 as 1. And second job as W2 is 3 and L2 is 10.
Let's see.
So
this, yeah, we'll do the second job first, then 1. This is 10, this is 11. So the objective is 10 times 3. 3 times 10 plus 2 times 11. 30 and 22. This is 52. What are the other option? Other option is there is only one more option. This is 1, this is 11. So 2 times 1 plus 3 times 11. Yes, so we have got a counter example. We have got an example where this approach of simply sorting the jobs according to their weights and do the highest weight job in the beginning is not correct. Does not lead to the correct solution, optimal solution, and this is the proof. Here is a counter example where the algorithm fails. Anyone has any doubt that this first approach is not correct? Is everyone clear that the first approach is not correct?
Yes, sir.
Now, this is what I mean by this warning. Most greedy algorithms are incorrect. And especially greedy algorithms, intuitively it looks correct. And especially if it is your greedy algorithm, it will be very easy for you to prove that it is correct. And that's what I mean by proof of correctness is non-trivial. And be very skeptical about proof of correctness. Read this very, very carefully. Every step, every line, whatever statement you write in the proof of correctness. To prove that something is incorrect is very easy if you are able to prove it. See, everyone is convinced. But in the beginning, some of your friend gave me a proof of correctness. I was convinced, many of us are convinced, sort of convinced, mini convinced, half convinced, 80% convinced. So that's why proof of correctness for greedy algorithm must be scrutinized and you should be very, very skeptical about it. You should read very, very carefully. To proof of incorrectness is very easy. Is there any one of you who believes or sort of 80% convinced that this fast algorithm does not work? No, it is clear like daylight that it does not work. Here is a concrete example. Here it does not work. Everyone with me? Have you understood my sort of these two highlights? Why most greedy algorithms are almost incorrect? You will see others are some others are also incorrect, and why it is non-trivial, the proof of correctness. Okay. How about the second one? First one is incorrect. Second one. What do you think? If you tell me yes, you need to give me a proof of correctness. Otherwise, give me a counter example.
Sir, I think the same example as the previous one is a counter example.
Correct. The same example will work. I will let you check. Okay. Third one. I'll let you check. Second example gives. And the second one, let me comment us regarding the second one. Second one also intuitively also does not make sense. Because, to do the jobs which has more weight, to the high weight jobs you should be doing first. That makes sense. But why the jobs which takes lot of time, whose length is very much, those jobs you should not be doing first, no? Because then that will not only that will delay, that will increase the completion times of all the jobs that will be done after that. Am I making sense? If some job has very high length, then we should not be doing that job in the beginning. We should try to do that job at the end. If I do that job in the beginning, and there are lots of jobs which are done after that job, after a lengthy job, then that lengthy job is sort of increasing the completion time of all the jobs that are following that job. Am I making sense? Anyone who is not able to follow? So in that sense, that third candidate sort the jobs by WI by LI sort of makes sense, make intuitive sense. Is it correct? Is it incorrect? Anyone? What do you think? Correct? Incorrect? Okay, we'll see whether it is correct or not. But you are now bit sort of, you have got a glimpse of what do I mean by non-triviality in the greedy algorithm, it's very easy to come up with greedy algorithms. And there are some greedy algorithms for which it is very difficult to find a counterexample. So some of the greedy algorithms will fail only for a specific, very stylized kind of examples. So those examples are very hard to find also. So yeah, so that's the both fun and pitfall of greedy algorithm. Okay, so now instead of telling you the answer for the third part, which looks correct, let me leave it at this point, and let me give you a systematic approach of how to tackle the greedy algorithms, how to approach, how to apply the greedy algorithm design technique for a problem. So first is that you should always try to make the problem, simple. In some sense, look at this problem. It has two input parameters, sort of, the lengths and weights. In assignments, you will see more interesting problems on scheduling, which has more parameters, lengths, weights. You can have say deadline or some more parameters. Now we have understood that this designing a greedy algorithm is not a trivial job. So let's give it a bit respect and try to sort of understand how the greedy algorithm will look at on some special cases. So to understand the special cases, there are various dimensions of the problem. There are two dimensions. One is length, another is weight. So let's understand how the greedy algorithm should behave with respect to one dimension. And to understand its behavior with respect to one dimension, I need to keep every other dimension fixed. It's like physics law. In every law, say Ohm's law, we assume that everything is fixed, although in reality everything can't be fixed at all. But if everything is fixed, everything else is fixed, then current is proportional to voltage. So here also, we don't have a algorithm yet, but let's understand how the algorithm should behave with respect to each of the domain, each of the parameter. So to understand that, we will keep all other parameters, all other domains fixed, sort of nullify all other domains. So here, the way to nullify other domains is that, for example, I want to study how the greedy algorithm will behave with respect to lengths. So let's assume that all weights are 1, all weights are same. If all weights are same, if you look at the objective function, if W1 equal to W2 equal to W3, then if these are all same, then this weight function does not matter. It's like all weights are 1. All it matters is length. Now can someone tell me, if all weights are 1, all weights are same, what will be the optimal schedule which will minimize the sum of completion times?
Least length done at last.
Excellent, very good, very easy. You see, very easy. Always start where you know something and go try to reach in step-by-step fashion to the place where you do not know. You want to your goal you go step-by-step fashion. So we know that whatever be the greedy algorithm, whatever be the optimal greedy algorithm, it must behave in the inputs where all weights are same. It should execute the jobs according to their increasing order of lengths. Convinced everyone? Similarly, let's understand its behavior with respect to weights. So assume that all lengths are same, all lengths are 1. Then how will it schedule the jobs if all lengths are same?
The greatest weight first.
Exactly, greatest weight. So with respect to each parameter, with respect to lengths, it should give priority to smaller jobs. It should execute smaller jobs first, and it should execute the heaviest weight jobs, high weight jobs first. Now we need to combine these parameters. So there are two very natural ways to combine. One way is the way that is mentioned in Wi by Li in the third point. That is one thing which combines both the effects. At least if this algorithm, I don't know whether it is correct or not, but if this algorithm at least performs the is, let me write this way, sort Wi minus Li. These also have the same effect. Everyone is convinced? So first, the first step is that you study the behavior of the optimal algorithm which you do not yet know with respect to each of the parameters. And now try to combine these parameters in some natural ways. Now, among these two, both of them cannot be correct. Why? Because it seems that there can be two inputs where the two approaches, two algorithms, third and fifth, will give rise to two different outputs. So we suspect that, and if this is true, that there exist inputs where these two different approaches will give rise to different outputs, then again it is very easy or try a natural approach is to look for those examples, so hopefully small examples, and in small examples we can by brute force find out what is the optimal, and again find out which among these two approaches is clearly incorrect. So let's try to construct an example of where these two outputs, these two approaches gives different outputs. So how about this example? Say L1 equal to 5 and say L2 equal to 2 and W1 equal to 3 and W2 equal to 1. What is say then here we should write W1 by L1?
0.5.
3 upon 5 and W2 by L2 half, yeah. And what is W1 minus L1? It is minus 2 and W2 minus L2 is minus 1. So that is good. This is exactly what I wanted. That if I look at Wi by Li, then I should do the first job first. This is the output of this way. The third approach outputs this thing. The first job first and then the second job. And the first job takes 5 units of time. Second job takes 2 units, so it's and finishes at 7. And the fifth approach executes the second job first, then the first job, and this finishes at 2, this is at 5. This is exactly what I want. Hopefully the objective functions are different. Let's see if the objective functions are same, then this is not an example to discard some approach. So what is the objective function here? W1 is 3 times 5, 15 plus W2 is 1, 7. This is 22. And what is this? For second job, W2 is 1, so this is 2 plus, this is not 5. This is not 5, this is 7. Right, because second job takes 5 units of time. 7 times 3, 21. This is 23. So we know which approach is incorrect. For which approach I have a counterexample?
Wi minus Li.
Yes, fifth one. So what I am trying to teach you is the approach. It does not in your real world problem. It can have more than 2 parameters, 3 parameters, 4 parameters, and this is how you should. This is one way to approach or reach the optimal algorithm. So this is the approach. This is the thing, and you can try to prove that this is not correct. And after trying, you will able to see that you are not able to find. You are not able to find any counterexample for that. Now, when you want, don't try too hard because maybe it is correct. It's like I have written what I've written. Most greedy algorithms are incorrect. It's not that all greedy algorithms are incorrect. Maybe this is a correct algorithm. So you need to prove it. And it turns out that this algorithm is correct. So theorem. That 3 is correct. Now, how do I prove it? Again, we should not, in proof, we should be very, very careful, extremely careful. And I am exhibiting you a proof technique, which is called exchange argument, which is very powerful and is often found very useful in proving correctness of greedy algorithms. Exchange argument. Okay. What is the algorithm? The algorithm is that sort the jobs according to Wi by Li and in say decreasing order and perform those jobs accordingly. So by renaming the jobs, let's assume assume without loss of generality that this ratio is highest for first job, followed by this. Why this is an assumption without loss of generality? Because I can rename the jobs. Whichever job has the highest W1 by L1, let's call that job the first one. The problem does not change if you rename the jobs. So because of renaming. So by renaming, without loss of generality, it made renaming. Okay. So for simplicity, again, you know that teachers only do simple cases. And you have seen that in assignments and exams, first class test also. That classes teachers teach only simple cases. Assume that there are no ties. You will handle the ties. Assume that there are no ties. So we claim that this is the optimal schedule. This is the schedule. That means do the first job first, second job next, and so on. This is the optimal schedule. This will minimize the weighted completion sum of completion times. So suppose not. Prove by contradiction. So suppose not. Suppose not. Then suppose not. Then let say pi be an optimal schedule. Okay. So pi is some schedule and which does not execute these jobs in this order. That means what? That means that in pi is a schedule. It performs jobs in some order and there will be a consecutive jobs like here is I, here is J, such that means J is performed immediately after I, but Wi by Li is strictly less than Wj by Lj. And these jobs are done consecutively. J is performed immediately after I in pi. Why such a pair of jobs must exist? Can someone tell me?
Because the first one is incorrect. W1 by
exactly. If this is not correct, that means what? That means if there is no consecutive jobs such that this condition does not hold, that means pi is sigma. Pi is, that means pi performs the jobs as this order W1 by L1 W in this order. So in pi, because this is not the correct one, suppose not this not, That's why in pi there must exist some things. What we do is that, can someone suggest what we do? How will I reach a contradiction?
We will show that if we change the ordering in that way that
Exactly.
it is sorted in correct
Exchange.
order, then it will become
Very good, very good. Exchange, the name says exchange argument. Exchange ing. Exchange the places ing. So let's consider pi prime. Everything is same as pi. Just exchange ing. So let me write C. That means cost of pi. C of pi prime is cost of pi prime. Can someone relate me cost of pi prime with cost of pi? For all the jobs which is executed before I, their completion times remain same in both pi and pi prime. We are not, those jobs are not touched at all. Convinced everyone?
Yes, sir.
All the jobs
Yes.
that are
Yes.
executed after J in this green block, their
That
completion
will
times are also not affected.
not
So
affected.
these jobs contribute same amount in both the sums, C pi and C pi prime. Okay. For I, okay. Now for I, completion time increases. How much it is increased? It increases by LJ. The completion time of I increases by LJ.
Yes.
And its contribution in the sum, so it's is increased by Wi times Lj. But the J, for J, its completion time decreases by Li,
Like
and its contribution is by Wj times L. Now what is this? From the assumption that Wi by Li is less than Wj by Lj,
it is
we
less
get
than
that
0.
this is less than 0. That means we have found another order whose completion time is strictly less than completion time of pi. So this is less than 0. This contradicts that pi. Then how come pi be an optimal schedule? This contradicts the optimality of pi. Everyone with me? So this concludes the proof. That means there cannot exist any such pi. Because if there exists such a pi, I can exchange and get a better schedule. Yes, tell me.
But why was there a need to exclude the less than equal to sign there? Like, even if it is equal to, now we can see that just changing the job does not make any sense. So we can do any job at first.
That I won't say. That is your homework. That I won't say. As I told, in class, teachers only teach the easiest things.
So my question is, does it make any sense, or like, will it make any difference?
Which one?
Or, including the equal to, like.
You think? I won't tell that.
Okay.
Optimal need not be that will make the proof wrong, because optimal may not be unique. Think of input instance where all job weights and all lengths are same. Then all permutations are optimal permutation.
Yes.
So optimal need not be unique. That's why I have written an optimal, not the optimal.
Also,
But-
so in our proof, like we took only 2 consecutive like entries.
Yes.
Shouldn't we consider 2 entries that are not consecutive as well?
What is the goal of my proof? What is the goal of proof by contradiction? The goal of the proof by contradiction is to contradict. You can consider different things, but to contradict the optimality of pi, I only need to find another schedule whose cost is less. That's what I have got. And this is one of the easiest way to find a another schedule whose cost is less than cost of pi, giving me the desired result. I want to prove that pi is not optimal. There can be many other different, difficult, not so difficult, easier ways to obtain another schedule, say pi double prime, whose cost is less than pi also. That will also be a proof. Am I making sense? The goal of proof by contradiction is to find a find a contradiction. In this case, find a schedule whose cost is less than the proposed optimal schedule, the assumed optimal schedule. Okay. TS, please take the attendance if you have not taken. Okay, in the next class, we will see Huffman code and some more things. So here there are various forms of machine scheduling problems in Codman book and many other books. You will see another problem called activity selection, where there is a the start time and completion time is also specified, and those things. Activity schedule, activity selection. In the reference books, you read various other problems on this scheduling. Those are actually various forms of scheduling problems, various variants. And you see how the greedy algorithms are derived. Exactly same high level idea, exact same this framework of proving optimality or correctness using exchange argument and so on and so forth. Question. In tomorrow's class, we will see more non-trivial and involved proof of correctness, which is our Huffman coding, where only exchange argument will not work. We will do some more work. But the algorithm we will see is very easy. Running time is very easy. Everything is easy except proof of correctness. Question. Feel free to leave. I am out of time. How was the question paper of exam class test 1? Easy, hard? Class is over. Feel free to leave. If you have any question, you can stay. If you want to